So now we start our first meeting of the seminar in this term with Roman Golovko, who should speak on tell me, Roman,
What?
the title of your talk.
On non-geometric augmentations and torsion in Legendrian Cohomology.
Thank you, Roman. Sorry, I remember only some Lagrangian and Theorem. A little bit how to say. Yes. So please, Roman. So that is here.
Yeah, so first of all, thank you for this opportunity, and it's always nice to give a talk at the Institute of Math. And today I would like to talk about some work that I basically started when I was in Prague-Hradec Králové a few months ago. So this work is on non-geometric augmentations, and as a side result, we will see also some torsion in Legendrian contact homology, algebraic torsion. And let me start with the motivation. So motivation. So basically, we'll consider the simplest contact manifold, let's say standard Euclidean vector space with a standard contact structure, namely we have a contact form dz minus sum of yi dxi, and which is written with respect to the standard coordinates x1, x2.
Yes.
Okay, so yeah, thanks. Okay, should I continue? Okay, great. So we consider the most basic contact manifold, which is a standard Euclidean space. Whatever I'll say today will work for more general ones when we consider just a Darboux ball. So basically in contact geometry, there is this principle that if you can do something at the level of standard Euclidean vector space, you can actually move it to more complicated contact manifolds locally, like in some, you can move basically these results to Darboux balls. Okay, so we'll consider the standard contact vector space. This is a standard contact form. I'll write it as alpha standard. The standard form is written with respect to the coordinates, I don't know, x sub 1, y sub 1, x sub n, y sub n, and z. And here we'll consider Legendrian submanifolds. So for us, Legendrian submanifolds will be closed. So they'll be closed and let's say orientable. And Legendrian, for those who don't know, means that so basically we have a contact form. This contact form gives us contact structure. I'll also write it as a xi standard, and Legendrian means that lambda is n-dimensional. And at each point, tangent space to lambda is a part of contact structure.
The basic example of the closed.
What?
Basic example, Lagrangian submanifold.
Yeah, so for example, yeah, so closed means basically compact without boundary. You can consider R3 with a standard contact structure, and I don't know, you can draw something like that in X Z projection. So if you have R3 with a standard contact structure, we have coordinates x, y, and z. We can take a projection into xz plane. I don't know, this is a standard unknot in the xz plane. So that's example. I don't know, I can draw more sophisticated examples, and actually during the talk you will see more sophisticated examples. Okay, but this type of notion can be, of course, extended to high dimensions. And once again, so Legendrian just means that we have something of dimension. So if our manifold is of dimension 2n plus 1, then here we will have something of dimension n. And the bin Legendrian means that the tangent space to our submanifold will be a part of a contact structure. And the motivation comes from the following thing. So basically to this lambda, you can associate some set, so generically finite set generically finite set of so-called reports, i.e. Integral trajectories of PDZ, which start and then on lambda, and then this set will be denoted by, let's say, q lambda, and also we can associate some algebraic object that we call a lambda, and this is so-called Chicano-Elliott algebra. Berg algebra. So this algebra gives us invariant, which can be seen as a version of the relative symplectic field theory, and it was first defined by Yuri Chichanov in dimension 3, namely for Legendrian knots, and then it was observed by Yakov Eliashberg and also given Talley and Hofer, who introduced symplectic field theory that basically this type of structure naturally appears there as well. And in R to the 2n plus 1, this invariant has been intensively studied by Ekholm, Nair, and Sullivan. Okay, so let me also put these names. Sullivan. So I will explain what is this guy in a few minutes, but in order to explain the motivation, I don't need it. Let me just say that this A lambda is a tensor algebra, namely it's a unital non-commutative algebra freely generated by the set Q lambda. And even if the set is finite, since we are talking about tensor algebra, namely non-commutative algebra, we will get something which will have which will be infinite dimensional, basically, even in every degree. So whatever we will see, so this A lambda is like a differential graded algebra. It's a DGA, and there will be some differentials, there will be some gradient. And unfortunately, because this algebra is a unital non-commutative, it is huge. And you know, whenever we will consider it, we will have basically infinite dimensional vector spaces in each degree. And yeah. What was that? Yeah, so these guys are usually called reports. So this reports are integral trajectories, as I wrote, of DDZ. So why reports? Because DDZ is basically a Reeb vector field. So it's a vector field which is everywhere transverse to the contact structure and with a property, with some normalization properties that So it has a property that basically its flow preserves contact structure, and also it's everywhere transverse to the contact structure with the normalization conditions that contact form evaluated at this vector field is equal to 1. It's easy to see that dz minus this sum evaluated at ddz is equal to 1, some normalization condition. Okay, so that's this algebra. So we have a Legendrian, we have this algebra. As I said, this algebra is difficult to deal with. So how to deal with it? Yuri Chichanov introduced a method of linearization. And that's a standard way that is used in symplectic and contact topology to deal with this algebra. Basically, it comes from the fact that this algebra in general is generated over some, let's say, R, where R is a, it can be non-commutative, but in this talk, it will be mostly commutative. So unital commutative ring, Okay. And what is this linearization? Basically, it comes by considering, so one get it if you get a DGA map from our algebra to the ground ring with a zero differential. Okay, so here we'll have some differential. Here we consider ground ring, and it will have a zero differential. And the unital DGA map like that is called augmentation, and it allows to linearize our algebra. Okay, so it's like a unital DGA map. And if we have this epsilon, then we can form so-called A lambda. Here we have a curly A, here we have a standard A. That will be something like a free R module. once again generated by this Q lambda, and we'll have some differential, which is a linearized differential. Since we have a finite number of elements, we will basically have a finite dimensional module. So it's we will have some invariance that's easy to compute. Okay, so existence of this epsilon gives us some computable invariance. Okay, and yeah, let me say that this a lambda leads to some homology, which is called the Legendrian contact homology. Here you will have linearized Legendrian contact homology. This Legendrian contact homology is a Legendrian invariant. That's a result of a Cohomology and Sullivan. Here, if you just fix one epsilon, unfortunately, we won't have Legendrian invariant. But if you fix all possible epsilons and you consider the set of all linearizations, then we get a Legendrian invariant. Okay, computable Legendrian invariant. Now, many augmentations come from geometric objects. So these geometric objects are so-called, so quite often, augmentations. So I need to write probably word augmentation here. Quite often augmentations come from geometric objects. For example, embedded. So, for example, embedded exact Lagrangian cobordisms. Lagrangian cobordisms. Okay. So embedded exact Lagrangian cobordisms, I will provide the definition slightly later, but basically you can think about this guy as a certain Lagrangian living in the original contact manifold times R, which bounds our Legendrian at infinity. Okay. Yeah, so whenever you have exact Lagrangian cobordism, you can cook up augmentation. So I'll explain. I will explain it. So this is just a motivation. Yeah. Okay. So while I say, for example, maybe it's better even to remove it here, but so morally speaking, so I can forget some of the words. So I say, for example, because sometimes I can forget about embeddedness. Sometimes I can consider immersed ones, immersed exact Lagrangian cobordisms. Also, there are some doubts about the word exact. So sometimes one can actually make this condition weaker as well. So one can consider not exact Lagrangians, but weaker things. Anyway, so quite often these augmentations come from geometric objects, and what we would like to do today, we would like to discuss augmentations that are not coming from these geometric objects. Okay, so we would like to discuss examples of augmentations which do not come from this embedded exact Lagrangian cobordisms. Okay, and besides that, let me say that here, so when we talk about this Chicano-Algebra algebraic homology, as I said, it's called Legendrian contact homology. I will write it as LCH, and here, whenever we have this complex, we will consider so-called LCH epsilon, where epsilon corresponds to the augmentation. This will be a linearization. And also today we would like to see what are the potential values, what is the potential geography of these linearizations. Okay. In other words, if you consider our algebra not over fields, so if you consider a field, of course, these guys will be just the vector spaces, right? So no torsion, no algebraic torsion is possible, but let's say if you consider z coefficients, okay, and integral coefficients, and we consider the augmentations into z, then we can ask whether it's possible to get an arbitrary, let's say, finitely generated abelian group here at this level. Okay, so this is one goal. The second goal, is it possible to get? So the second goal is to answer the following question: is it possible to get an arbitrary finitely generated abelian group at the level of LCH epsilon, namely for this linearized complex. Okay. Okay, so this is a motivation. I hope it's clear. Now let me get to some details. Okay, so I mentioned this algebra. I'll spend 2 minutes explaining this, what this algebra is. I'll explain what exactly Lagrangian cobordism is. I'll explain what type of obstructions for the existence of for being non-geometric or for being geometric exist for the augmentation. So what type of properties, what type of geometric somehow identifications of what type of basically properties that show that augmentation comes from something geometric exist in the literature. So let me start with the notion of Chicano-Algebroic algebra. So A lambda. Once again, so I said that this is a unital non-commutative algebra freely generated by this finite set Q lambda. So non-commutative DGA freely generated by Q lambda. And let's say, so in the definition, I'll use a simple coefficients. I'll use Z2 coefficients. One can consider, of course, more general coefficients. And at some point, we will consider Z coefficient because we would like to answer the second question in the motivation. But just for the definition, I'll use Z2 coefficients. So basically, I won't say too much about gradient, but I'll explain the differential. So differential, so for those people who know, basically this gradient comes from so-called Maslov index, or kind of Maslov index or Conley-Zender index that one can associate to this reed chords. And differential is basically given the following way. So let's say if you have these chords C and C plus and C1 minus, CK minus. Okay, so if you consider this collection of reed chords, then we can define D of C plus to be a sum with respect to C1 minus CK minus, such that the dimension of the moduli space, so I'll write and then I'll explain, of holomorphic disks with positive puncture at C plus and negative punctures at C1 minus CK minus equals 1. So here we do computation of the number of elements here, right, in this moduli space. And we take quotient by R, C1 minus, CK minus. Okay, so here we'll have some formula. Let me explain what appears in this formula. So basically, we consider disks let's say disk D. This is a disk in the standard complex line, and we remove some points on the boundary. Okay, so we remove some points. Let's say we remove point X, we remove point Y1, Y2, blah blah blah, YK. Okay. Now here we have a standard complex structure I on C, and we will map these guys to R times R to the 2n plus 1 with the symplectic form D e to the S. They want to use S or T. Let's say T. D e to the T alpha standard, where this is the T direction. Okay, so I take my contact manifold, I take a product of this contact manifold with R. So what do I do with these disks? I will map these disks in a holomorphic way such that the boundary of this disk will live in R times lambda. Okay, the boundary will live here. And these removed points will be asymptotic at positive infinity and at negative infinity to some ripcords. Okay, so point X will be asymptotic at positive infinity at C plus, and points Y1, Y2, blah blah blah, YK will be asymptotic at negative infinity to chord C1 minus, blah blah, CK minus. Okay, and the boundary once again is on this cylinder. Yeah. So here I have some almost complex structure, capital G. And what's that? I remove some points. So basically, I consider a disk with boundary. I remove some points on the boundary. Yeah. And here, this is almost complex structure. Complex structure satisfying some compatibility conditions, and our map U is IJ holomorphic. In other words, it satisfies Cauchy-Riemann equation with respect to I and J. Okay. So now D of C plus is a count of the number of elements in the moduli space of such disks, is a property that this modular space has dimension 1. So it should have some geometric structure, first of all. It has a dimension 1. And also, why do we have a quotient by R here? Okay. So the point is that if we have one such holomorphic disk, we can push it into T direction. So these translations in T directions, in T direction will keep it holomorphic. So basically, there is this free action by R. We can take a quotient by R. If this guy was one-dimensional, after quotienting by R, we will get something zero-dimensional. Also, there is a Gromov compactness theorem saying that whatever we will get here is a compact zero-dimensional manifold. Compact zero-dimensional manifold means finite number of points, and we do count mod 2. Okay. So D of C plus is some number times some word. Okay. Now, so what are these exact Lagrangian cobordisms and exact Lagrangian filaments, and what is how to get augmentations out of those? So this exact, so I'll explain what the notion of exact Lagrangian, let's say, cobordism, and then the notion of filing will come automatically. So exact Lagrangian cobordism. Basically, if you have two Legendrians, let's say lambda minus and lambda plus, in R to the n plus 1 standard with a standard contact structure, two Legendrians. So we say that lambda minus is exact Lagrangian cobordant to lambda plus. And I'll write L here. So there is exact Lagrangian cobordism L from lambda minus to lambda plus. If and only if. So when I write like this means that there is exact Lagrangian cobordism. Lagrangian cobordism from lambda minus to lambda plus cobordism L. So if and only if there is a cobordism L lambda minus lambda plus. So there is a cobordism. And the symplectic, and an exact Lagrangian embedding. Exact Lagrangian embedding. Lagrangian embedding of this L lambda minus lambda plus to essentially this guy. Okay, R times R to the 2n plus 1 with this symplectic form. So for simplicity, I'll write it as S R to the 2n plus 1 standard. This means symplectization of our compact manifold. Okay, to symplectization. Okay, said that. So first, L restricted to, here we have this T coordinate. So T infinity times R to the 2n plus 1 is equal to T infinity times lambda plus L restricted to minus infinity T times R to the 2n plus 1 is equal to minus infinity T times lambda minus. Okay, so what it means is that basically, so here we have this extra T direction. So if you restrict ourselves to the I need to put minus T. If you restrict ourselves to this portion, right, and to that portion, our Lagrangian L will look like a cylinder over Legendrian. Here we'll also have something which will look like a cylinder over Legendrian. Okay. Also, this embedding is proper. So we would like to say that this guy is proper. So this embedding is proper. Is proper, i.e., basically L restricted to, I don't know, minus T times R to the 2n plus 1 is compact. Okay. Potential with some topology. Now, what do you mean by Lagrangian? Lagrangian means that our symplectic form vanishes on our L. Okay. And what exactness mean? So exactness here, exactness. So maybe just to say Lagrangian means that our form is omega standard. This omega standard on L is equal to 0. And exactness means that this symplectic form has a primitive, right? Namely e to the T alpha standard. Okay. So exactness means that e to the T alpha standard is equal to d of f for some f in C infinity L. Namely, there is a smooth function on L, not of course in the symplectic manifold, because if you have some function of the symplectic manifold, then you will have d of something, so you will get something automatically 0. But we have some function on the Lagrangian with the property that d of it is equal to the primitive of the symplectic form. Okay. And there is one extra slightly weird condition that we would like this function a priori on these ends, on these cylinders, is locally constant. But we would like to says that this function in fact is constant. What?
Simplistic form, it's a simplistic form of simplistic manifold and any function on the Lagrangian.
Yes.
Lagrangian is only half of the.
Yeah, Lagrangian is half dimensional. Yes.
Yeah. So they.
So half dimensional. You mean here?
But not in the years. So
What? What?
Because it's a function.
So you ask what do? You ask me what this means.
Say infinity of n, the smooth function on Lagrangian manifold.
It's a smooth function defined on Lagrangian manifold. Yes.
But if you want to say that in neighborhood of Lagrangian manifold, it's a simple morphic to symplectic manifold. So Einstein theorem, yeah.
No, but I mean, well, here, I mean, why do we need Einstein neighborhood theorem?
Because
What?
how to say that differential depend on the Lagrangian.
No, but a priori, what you can say, you can define the notion of smooth functions basically on arbitrary set using the standard shift theoretic construction. What?
So that's I also know going into given guidance, abstract theory or something like that. But
Yeah.
what I mean, that's what I say. That's a function is defined on L, and that means differential is defined also L, and everything is in symplectic manifold.
Yeah, I mean, okay. So if you want me to write this way, I can write it this way. Yeah, but because otherwise it does. Yeah. I mean, otherwise it doesn't make sense if f is differential. Yes. Yeah. I'm not talking about extension or whatever. Yeah. Of course, you want to say this. Yes. Yeah. Sure. Yes. Yeah. Does it make sense?
Yeah.
Perfect. Yeah. Thanks. Is it clear?
Yeah.
Okay. Good. No, sure. Yeah, you can do many. Yeah, but here. Okay. Great. Yeah. So basically, this type of condition of being constant and not just locally constant, it's not important if you consider Legendrians that are connected. But if there are Legendrians with several connected components, then a priori this f is just locally constant. And in order to control its values, if let's say you would like to glue cobordisms, it's important to say that f is constant. Okay, so anyway, there is this notion of exact Lagrangian cobordism, how it leads to augmentation. Okay. I will leave this formula. Now. So basically, if you have this guy, so here we have this notion of exact Lagrangian cobordism, right? But this type of definition is so can be considered in the case when lambda minus is empty, when there is no negative end at all. So if you have something like that, okay, then if you don't have negative end, this exact Lagrangian cobordism will be called exact Lagrangian filling of lambda plus. Okay, so if there is no lambda minus, or in other words, or lambda minus is empty, then we get exact Lagrangian filling. Now, how to get this epsilon, and then I'll explain also why I would like to keep this formula. Okay, so how to get epsilon out of this L? Here we have this lambda plus, or I'll just write lambda since we don't have any lambda minus. So here we have lambda, here we have L. Yeah, and in order to get epsilon, what we do, we consider basically once again so similar type of moduli spaces, but we will consider moduli spaces with of holomorphic disks with only one removed boundary point. Okay, namely we'll consider holomorphic modular space of holomorphic disks with one removed boundary point that will be asymptotic to the ripcord, and this ripcord will be C+, and the boundary will live on L. Okay, before our boundary of holomorphic disks, they live on the trivial cylinder over Legendrian, right? They live on this R times Legendrian. Here we have something that looks like a cylinder only near our Legendrian. The rest is some non-trivial exact Lagrangian filling, and we consider the space of holomorphic disks with a boundary on this filling. Okay, so this epsilon C+ will be just, I don't know, the count of the number of elements mj of C+. Okay. Now you can say, why don't we have this quotient by R? Because it simply doesn't exist. In the previous situation, we had this trivial cylinder with an honest translation in T direction. So if you translate holomorphic disk, it remained holomorphic disk. Here, of course, since it's possible to have non-trivial topology and we don't have triviality of this filling, we have this compact part and blah, blah, blah. We do not know a priori whether, it will remain holomorphic or not. So we do just this proper count. Okay, so that's a way to get this, these augmentations. Now, what are the obstructions for augmentation to be geometric or non-geometric? Okay. So I'll basically mention two obstructions, maybe two, maybe three, so we'll see. So obstructions. So obstructions of, let's say, geometricity. So maybe I'll mention three. So the first one, and the first one is the simplest one, and it will work actually not just for exact Lagrangian fillings, but also for just general Lagrangian filling. So we don't need the notion of exactness here. So basically, existence of a filling of L will imply that, oh, I need to be careful, will imply that TB of lambda is equal to 1 second. So it will be 2G of L minus 1 or something like that. Anyway, so here, so what we have here, oh yeah, maybe I'll even, sorry, let me write it this way. TB of lambda is equal to plus or minus, okay, so plus or minus, this guy depends on dimension. And then here you will have P of L. Okay? So TB of lambda is equal to plus or minus Euler characteristic of L. TB of lambda is some numerical invariance that you can relate to lambda. Okay, so if you wish, okay, so I won't provide the definition, but it's some number. You won't use this abstraction. Basically, I just want to say that there is some numerical abstraction. So some numbers that you can associate to lambda is equal to plus or minus Euler characteristic of L, where this plus or minus depends on the dimension of our lambda. Okay, so this is the first abstraction, and it works not just for exact Lagrangians, but for Lagrangians in general. Okay, so works for general Lagrangian fields. Lagrangian fields. And if one asks who is responsible for that, I should say probably Baptiste Chantrain. He wrote it in dimension 3, where so you can write it in terms of genus of a surface if our Lagrangian is surface. So I first wrote some formula using G, and genus was a genus of a surface. Of course, earlier characteristic in dimension 3, like for Legendrians in dimension 3, Legendrians are one-dimensional, hence Lagrangian fields will be two-dimensional. Hence, earlier characteristic can be written in terms of genus for orientable Lagrangians. Yeah, so one can write some formula using genus for orientable Lagrangians. Okay? And it's due to Chantrain in dimension 3 in high dimensions. Okay, I wrote something at some point, but okay, it doesn't really matter. There is abstraction like that. The more important abstraction is so-called Seidel isomorphism. Seidel isomorphism. Some people say not just Seidels, but the isomorphism of Seidel, Ekholm, Dimitrov-Glow-Rizov. Why? So basically, it says the following. So let's say if you have lambda and we have exact Lagrangian field L, so L is exact Lagrangian. Now we need exactness. Lagrangian. Okay, maybe I need to say, okay, so I'll say some words. Maslov number 0. Maslov number 0. Okay, some technical condition, some extra technical condition. So if you have exact Lagrangian field with Maslov number 0, then this linearized Legendrian contact cohomology of lambda with z coefficients, with z2 coefficients, is isomorphic to the singular homology of L with z2 coefficients. And now for dimension, here I need to write n minus I and here I. Okay, so what is this guy? Right, so here it's clear, okay, we have just singular homology of the field. What is this guy? And for that, I need actually that formula, okay? You see here we have a formula for the differential of the algebra. So what is the differential of the complex of this linearization, okay? The differential of the complex can be written the following way. So we just write d epsilon c plus. We add one extra sum here with respect to some index inside this word, where here we act by epsilon on all letters by 1. Okay. We had a word. Now we just associate some numbers to all letters by 1, and we have some indexing, basically, some index which corresponds to the position, basically, of the letter in this word. Okay. So this is this linearization, right? And this LCH epsilon lambda is basically this A lambda that I wrote, this in this case Z2 vector space generated by Rib quartz with this differential. Okay, this is a homology of this guy. Right? Now here I put epsilon on the bottom and some index on the top, which means that I'm talking about cohomology. So like in what sense cohomology? One can take not just this complex, but algebraic dual to it, like a stupid algebraic dual where you map everything to Z2. So here we have Z2 coefficients, you map everything to Z2. And this is basically cohomology of the dual complex. Okay. Make sense? Makes sense. So this is a Seidel isomorphism. As you see, this type of abstraction is really strong. So somehow the topology of the feeling tells us what should be the homology, this linearized Legendrian contact cohomology with respect to lambda, with respect to epsilon, like what it's supposed to be. Now you can say, I mean, what is this epsilon, right? How we get it? This epsilon is precisely the epsilon coming from this feeling. Okay, but here epsilon, this guy is so this augmentation coming from the feeling. Coming from L. Okay, so this is a Seidel's isomorphism. It was first introduced by Seidel. So it was his observation, basically. Then Tobias Ekholm provide let's say, a strategy of proof of this isomorphism, and then Yorgos Dimitroglou-Rizal finished this proof with Z2 coefficients, and then there are like many other people who actually did the extension of this result, so one can play with more sophisticated coefficients. So, and the next abstraction that is important for us is a abstraction of Gao and Rutherford. It's, well, we'll see how it goes. Yeah. There is abstraction due to Gao and Rutherford, and it's like it's written in terms of some algebraic varieties, basically, and maps between algebraic varieties. So there is an abstraction due to Gao and Rutherford. Gao and Rutherford. So let's say we have lambda and we have L, okay? The same type of story. Now, you can write H1 of L. H1 of L is a abelian group, okay? Let's say everything is compact, blah, blah, blah. So we consider we have like a finitely generated abelian group. And I don't know, it can be written, let's say, as ZK plus ZK1 plus ZKS. So we have a free part and we have some torsion part, okay, as usual. Now we can relate to this L and to this H1L some algebraic variety. So we can define, we can relate so-called OG-LF, where F is a field. Let's say algebraically closed. It's a field, yes. F star QK plus CK1 F plus CK, let's say F, where CKIF is given by the set of points X, such that X to Ki is equal to 1, and X is in F. Okay. So basically, we can relate some algebraic variety. And okay. This is a so-called augmentation variety. And also, as it turns out, to lambda, you can associate some augmentation variety. So to lambda, what's that? It's just a construction. So far, I just provided some construction. I have L, H1 of L looks like that. I can write this formula. Yeah, okay. Okay. So to L, I can always we can associate also some variety. We can associate also some variety og lambda F. So now it's less constructive. Okay, so to lambda, we associated the Shtcherkanov-Aleshberg algebra. We provided definition over Z2, okay, over F2, if you wish, of that, over field which is simple. In general, one can define the augmentation over F, let's say pi1 of lambda. Maybe sometimes even not F, but Z. So for some group ring, right? So one can define some Shtcherkanov-Aleshberg algebra over this group ring, where this group ring actually lives in gradient 0, in the gradient component 0. And the point is that, so what is this augmentation variety? This augmentation variety is basically the extension of all maps. Okay, so one can write this guy, or one can write H1 of lambda, especially if this guy is abelian, you can always write it, but if it's not abelian, then one can do something, but one can, okay, so one can do coefficients over this ring, over this group ring, or over F H1 lambda over Z H1 lambda. So I will write, say, H1 formula here, and I'll use it for this augmentation variety. So basically one can, let's say like this, if one has epsilon for this algebra over this group ring, okay, if there is epsilon for the Chicano-Algebra algebra defined over this group ring, right? Then basically there is a natural map to the F, so to F. Coming, let's say, from some local system or something like that. So if you fix some local system, then we have this type of map. And basically this augmentation variety, it is a Zariski closure of all maps like that, which extend to the maps of the, which extend to the honest augmentations. Okay. So basically this augmentation variety is a Zariski closure of all maps of this type, which can be extended to the augmentations to F, okay, of the Chicano-Algebra algebra. So I didn't provide the proper definition, but this is pretty much how it looks like. And this Gauss-Rutherford obstruction says that if there is exact Lagrangian field, then there is a injective algebraic map between the existence of a field, exact Lagrangian, will imply that there is a map from augmentation variety of L to augmentation variety of lambda, which is a injective algebraic. So this is an injective map between injective algebraic map between two augmentation varieties. Okay. Great. So we would like to hook up. So this type of obstruction is more sophisticated than this one. So there are some augmentations for which we cannot say that they are non-geometric because of this formula. So for example, here we compute some this linearized Legendrian contact cohomology, and we see that, you know, in some degrees that correspond to the negative degrees here, we have something non-trivial, right? Then we can always say that, okay, so there is no exact Lagrangian field, because if there is one, we will have some non-negative negative degree here, right? Non-trivial, which is impossible by topology, basically, right? So one can find Legendrian submanifolds and augmentations which do not satisfy this guy. And also one can find Legendrian submanifolds and augmentations which unfortunately satisfies this guy, but do not satisfy this one. Okay. So in other words, this obstruction is more sophisticated than that one. Okay. And let's talk about these examples in low dimensions and in high dimensions. Let me just, yeah.
Think about TB as
TB. Well, yes. Yeah, TB is so-called Thurston-Banach number. Yes, in a sense, you can see it this way. So it's basically error characteristic of the linearized Chicano linearization of the Chicano-Algebra algebra. You can see it this way. In general, I mean, it can be formulated just, you take a Legendrian, you take its slight push in the rib direction, and you consider the linked number. And yeah, of these two guys. So that's, yeah. Is it clear? Okay, so we have these two abstractions. Let's talk about some examples. It's a pity that I have only 2 boards, but such is life. Yeah, so what comes to this abstraction of coming from Seidel's isomorphism. So Seidel's iso gives a called class A of Legendrians. So I'll call like Legendrian submanifolds for which there is an augmentation such that Seidel's isomorphism doesn't work because of some topological reasons. Class A of Legendrians, and this type of Legendrians can be found, let's say, in the Legendrian atlas of N, and made. So in particular, one can find some mirror of A21. So it has a Poincare polynomial, one of the Poincare polynomials of the form p to the -1 plus 4 plus 2t. The Poincare polynomial can be seen as basically, so the coefficient is a dimension of the corresponding vector space when we consider Chicano algebraic algebra over Z2 in the degree, which is the power of this monomial, right? So basically in the degree -1, we will have something of a dimension 1. In degree 0, we will have something of dimension 4. And in degree 1, we will have something of degree 2. Okay. So in other words, we have this Legendrian. We will have some epsilon. And for this epsilon, we have this Poincare polynomial. Okay. So from Seidel's isomorphism, basically we can say that LCH -1 epsilon is F2, right? And hence we can say that H2 is F2 of the potential Lagrangian. Yeah. And since here we have basically a 2-dimensional Lagrangian, right? Orientable, whatever, blah, 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 Lagrangian. And it's this Lagrangian is something with cylindrical end, or if you cut cylindrical end, this is something with boundary. This type of formula is impossible because of just algebraic topology from the algebraic topology point of view, right? One can find many other examples in low dimensions, like many other examples. In particular of this type, there is a Legendrian representative of node 946, 948 in the same table, in the same paper of N and Schoenstein made, for which these Poincare polynomials are such that, you know, Lagrangians, potential Lagrangians that should provide augmentations do not satisfy Seidel's isomorphism. And also for the class, for this Gao and Rutherford abstraction. We have, let's say, this guy. So this is one of the Legendrian examples of the one of the Legendrian representatives of the twist knots. One can have so-called lambda n, so this Legendrian representatives of twist knots. One can take here we have the picture of lambda 7. This is the XZ projection of some Legendrian knot, Legendrian twist knot. It has chords A, B, E0, blah, 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 E7, and C1, blah, 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 C7. Okay, so chords in degree 0 are A, B, C1, Cn, chords in degree 1 is E0, En. Okay, and if one computes the linearized Legendrian contact Cohomology, then it's possible to have that A0 is Z, H1 is Z2. Certain Banachine number in this case is 1. So somehow all these values are okay from the point of view of Seidel's isomorphism. And if you consider, we take Legendrian of the form, so we map A and B to 0, E1, En to 0, and C1, Cn to 1. Okay. Now, for this type of guy, we will have that augmentation variety, the Aug of lambda f is essentially, this is so-called V, which consists of A and B, such that A times B cannot be equal to 1. So you can, augmentation variety is algebraically equivalent to the set of such guys. And so here A and B and I and F. And Aug lambda Aug LF. So here we know this certain Banachine number. Certain Banachine number, as I said, basically is related to this Euler characteristic of Lagrangian. We know that in dimension 2, Euler characteristic is determined by the genus. So we can say what is the genus? Genus must be equal to 2. And sorry. Yeah, okay, let's say like this. The dimension of the first singular homology must be equal to 2, which means that the genus must be, so it's 2G minus 1. Yeah, so genus must be equal to 1 in this case. Yeah, so genus must be equal to 1. And augmentation variety of LF is F square, okay? And so basically Gao and Rutherford shows that there is no map like that, like an injective algebraic map from this F square to this type of augmentation variety. Now this is in low dimensions. Unfortunately, do I have like 2 minutes?
It's
Oh, it's
a lot of the, yeah.
okay.
Okay,
Okay, so yeah, so we will basically extend these examples to high dimensions. Okay, so we have these low dimensional examples, and we will get high dimensions, high dimensional examples out of those. Okay, and unfortunately, in Legendrian world, the only reasonable way to go to high dimensions is using some torsion of suspension. So we will play with of suspensions. So we'll basically play with the suspensions. So okay, so Legendrian suspensions. Suspensions response. They'll provide the formula for this simple suspension as one suspension, but the formula for more general one, I'll explain how to get it. Okay, so basically, if you have lambda, you can associate to this lambda, let's say lives in R to the 2n plus 1. You can associate sigma SM lambda, which will be a Legendrian submanifold in R to 2n plus m plus 1, which will be diffeomorphic, diffeo lambda times Sm. Okay, how? So we have lambda in R to the 2n plus 1. We take some parameterization of it. Okay, so we take some x1 we have some parameterization I, where basically to P we associate x1P ZP, okay, all the coordinates. So we assume that x1 of P is greater than 0. Yeah. Why? Because we have a contact form dz minus yi dxi. There is this dxi if we have a compact Lagrangian, Legendrian, and if we push it in the x1 direction, right? It's compact. We will at some point always have a situation when x1s will be positive, and this type of pushing is a Legendrian transformation because, as I said, in the formula for contact forms there is no x's, but there is only like dx's. So dx1 changing like this type of translation in x1 direction is fine. So we can translate it always so that we have this guy, and then we can the stupid suspension, the S1 suspension is basically. When we consider here, let's say we have a this xz projection for lambda of the form x1p, xnp, and zp, okay, and the xz projection for sigma s1 lambda will be of the form x1p sine theta, I don't know, cosine, let's say cosine, cosine theta x1p, sine theta, blah, blah, blah. Basically, we add one extra spot and we write basically the equation of a circle with radius x1 and with one extra variable theta, right? One can play the same game, and here we will have some xz projection of something which is like of higher dimension, and we can always lift it to the contact manifold of one dimension, of 2 dimension higher, right? So we had something in dimension 2n plus 1. We have this type of situation, which means that we add extra x variable, right? If you have extra x variables, there is also y variable when we lift it. So hence we will have something in dimension 2n plus 1 plus 1. Yep. And how to get the general formula? Basically, one can write the equation of a sphere. Okay. So here we will have like more angular coordinates, and we add more variables, and we write the equation of a sphere with radius x1, and the rest will be just a standard spherical coordinates for the sphere of dimension m. Yep. So this way one can get this sigma SM. Okay. Now, this type of construction is nice because it allows one to control Legendrian contact homology. And there is a structural result for that, which is due to Dimitri Rizal and myself. Basically, one can say that so if you have lambda and we have this sigma sm lambda, then in terms of rib chords, we can find the following correspondence. So here we have q lambda, all rib chords from lambda. Here, this guy, after certain Legendrian isotopy, we can say that it looks like lambda times the zero section in the cotangent bundle of Sm. Okay. So basically, here we have q sigma Sm lambda. And basically to one chord here, we have the whole Sm family of chords there. Okay. And after Morse transformation, we can in fact use the splitting. So we have this here. We have this here with a north pole and south pole. We have a Morse perturbation. So that basically to the Sm family, we relate the family that is indexed by the critical point n and by the critical point s on the sphere. Namely, to C here, we associate CS and we associate CN And this correspondence is of the following sort. So the degree of C is the same as degree of CS. And here the degree of Cn, sorry, yeah, all right, CS and here C. And the degree of Cn is equal to degree of C plus M, okay? Yeah. So we have this type of correspondence, and there is a map of DGA's inclusion here and projection there. So where here you have basically ideal generated by this n chords, and this guy is in fact isomorphic as an algebra to a lambda. Okay, so basically there is an inclusion map of this algebra, so we can include a lambda inside this a sigma sm lambda, where we map chord C to the chord CS. Okay, and then there is also this type of map can be inverted basically by some projection P, so that I composed with P composed with I is equal to the identity. Okay. This map in particular, this way in particular, we have a one-to-one correspondence between augmentations. Okay, so if you have some augmentation here, you can take a pull back here, right? And if you have augmentations there, you can pull back here, pull back there. Since it's left inverse, then we can actually have one-to-one correspondence between augmentations. Okay. So this is basically the structural result for the Chkhanov-Aleshberg algebras of the spans. And this way, like also for spans, there is a version of Kernet formula. Okay, so there is a Kernet formula. So for S1 span, we did it with Yorgos. For high dimensional ones, when the dimension is really high, so what's that? Kernet. It's I mean, this suspension is in a way product. Okay, so basically this will be something like a LCH epsilon I sigma SM lambda is isomorphic to LCH of epsilon I lambda plus LCH I minus M epsilon lambda. So there is, yeah, so we prove this formula. This formula is known for M equals 1. We did it with Yorgos some time ago. Also for higher M, like let's say if M is bigger than so-called action window for Legendrian, I did it and we are working with Yorgos like on the general formula. But the main point is that this type of formula allows one to control the linearized algebra of the span when you know the linearized algebra of the low dimensional Legendrian. Okay. And since I don't want to take too much of your time, I would like to say that basically this formula allows one to translate the Seidel's isomorphism and obstructions to translate Seidel's isomorphism. And to say that, let's say for this mirror of like that. This Kernet formula plus the fact that sigma SML. So first of all, there is a, so if you have lambda, we take a span of it, there is also, and there is a filling, there is also a span filling. And there is a span filling which is also isomorphic to SML, namely fillings can be lifted. So this Kernet formula plus this type of fact allows to extend the abstractions coming from Seidel plus this Gall-Rutherford for this twist knots two SM spans. Okay. So without too many details, but this is basically just algebraic topology. So this coordinate formula, if you have some properties of LSH lambda, the corresponding properties that didn't work, let's say, that allow Seidel's obstruction to fail, then this coordinate formula plus this type of lifting property will tell us that will tell me actually that the Seidel's isomorphism will also fail for the span, and the same will come to this Gauss-Rutherford story. So this is one thing, and what comes to this algebraic torsion, I will not write it, but I'll just say it in words. So this Seidel's isomorphism, one can prove it for Z coefficients. For Z coefficients. In this case, you can relate this linearized Legendrian contact cohomology with Z coefficients to the singular homology with Z coefficients. And of course, in singular homology with Z coefficients, one can have algebraic torsion. And then what one need to do, one need to construct some Legendrian submanifold, which has a filling whose, let's say, first homology is first singular homology is an arbitrary algebra, is an arbitrary finitely generated abelian group. And this way one will be able to get this algebraic torsion part. So this construction comes from so-called two-copy construction. So one can always take a Legendrian of complicated topology, take its two-copy. This two-copy will have an exact Lagrangian filling, which is a cylinder over original Legendrian, namely it will have the same topology, and this way one can cook up this augmentation. So thanks a lot for your attention. Maybe it wasn't too detailed, but I can answer questions.
So Roman, you have very nice picture of knots for the Lagrangian knot, right? Yeah. That is but then it means that now you have to construct new invariant because it computes the knot, yeah. No,
I didn't construct new invariant. Basically, so what I did, I found some examples in high dimensions of Legendrian knots with augmentations that are of non-geometric nature. I didn't compute, I didn't make any new invariant. These abstractions, they, in fact, so they're supposed to work in all dimensions. As I said, the Seidel's isomorphism is not due to me. It's due to Seidel Ekholm and Dimitrov-Glow-Riesel. This abstraction with this algebraic varieties is due to Gauss and Rutherford. The problem is that in high dimensions, it's like not many. There are like not many examples that can be computed in a natural way. Somehow, like in low dimensions, this Chicano-Algebra algebra is combinatorial, so many things can be done even with a computer. And one can study questions about geography and things like that. In high dimensions, unfortunately, it's not the case. So somehow, you know, people like examples, and you know, this type of lifting story just allows you to say that if there was Lagrangian, there will be Lagrangian. Like if there is a filling, there is a Lagrangian filling in high dimensions. If one talks about spans, but you know, a priori we do not know whether there are like, you know, if there is some augmentation, let's say for the lower dimensional Legendrian, we spin it. We will have some augmentation coming from this type of correspondence. As I said, we can translate between these augmentations, right, of a span and of the original Legendrian. But a priori, you know, if you don't know coordinate formula, you cannot say whether this type of augmentation is geometric or not. So there is no way to say that, you know, if you have that there is no Lagrangian filling in low dimensions, there is no Lagrangian filling in high dimensions. One cannot say much. But with the coordinate formula, one can actually say quite a lot. One can classify basically exact Lagrangian fillings in high dimensions, at least for spans coming from the algebraic topology information of the about exact Lagrangian fillings of the like in low, like for low dimensional original Legendrians. I don't know whether what I said is like very clear, but I didn't construct any new invariant. I use the known invariants, but for some particular Legendrians for which we know the structural result about Legendrian contact homology, for which the behavior of Legendrian contact homology is understandable. Because the problem is that in high dimensions, Legendrian contact homology is not combinatorial at all. as you see, like we need to deal with some Cauchy-Riemann equations. We need to deal with certain moduli spaces, and to write down these moduli spaces and to understand what's going on is a very difficult task.
Yes.
Okay.
Okay. If there are, yeah.
Sure.
So was would be quick to follow everything, but
Yeah.
when you gave these, what I understand are necessary consequences of having this geometric pattern.
Yes.
Right? So you
Yeah.
call them obstructions.
Yep.
Because if you can find some example of augmentation that doesn't satisfy these properties, then it's not geometric.
Yes. Yeah. Exactly.
But how do you recognize that these conditions are actually violated? And you said that like what these vitals as isomorphisms, you can look at a range of degrees, and then if there's non-geom cohomology outside that range, then
Yes. There is a trivial violation,
yeah,
and what comes to this injective algebraic map once again. So quite often it's just a story about, okay, so you have let's say by some God-given information, you know how H1 is supposed to look like of your potential filling. Let's say in dimension 1 for knots, as Gao and Rutherford did, they knew this information. They knew about the genus of the potential filling just from this certain Banachine number. If they know this G, they know H1, and hence they know how this augmentation variety of the filling looks like. Okay. In my case, I didn't know a priori what should be or what would be the H1 of the filling, and that's the reason why I need this Kernet formula. Somehow this Kernet formula, since I know how this filling is supposed to look like in low dimensions, and there is a Kernet formula plus Seidel's isomorphism, I can say how it's supposed to look like in high dimensions. You know, so there is a control, certain controls that allows you to say what will be this variety somehow for the potential filling, and then you know how this variety for the potential filling looks like, and you can say for sure how the augmentation variety for the Legendrian looks like, and then you can basically translate this, you know, non-existence of injective algebraic map of Gao and Rutherford in the trivial way to the span that I take. So basically, the augmentation variety of a potential filling will be the same in low and in high dimensions, and for the augmentation variety of the span of a Legendrian, one can show that it will be the same as augmentation variety of the original Legendrian. Okay. So somehow non-existence of injective algebraic map in low dimensions will give you non-injectivity of algebraic map in high dimensions. Okay.
So you still need to use some ad hoc.
Yes, and this additional information, yes. So it's supposed. So basically, you need to have some God-given information about the potential about the topology of your Lagrangian. Okay, so if you don't have it, then of course you cannot use this abstraction. And this God-given information in this case is given basically by the information about the Lagrangian in low dimensions plus this Kernet formula. Okay.
And so suppose that you find an augmentation that appears to satisfy, say, all these necessary conditions that respond to some filling, but does it follow that this filling exists, that it comes? No, so there are ways it's not.
So just abstract, yeah. So basically, these are just the properties. So if you have feeling that this feeling will give you this and this and this, the list of properties. This property with this certain Banachine number relating to the earlier characteristic is the simplest one, the most basic one. Then the next one is Seidel's isomorphism. Then after that, there is also results that I didn't mention of a Coleman-Likili relating A-infinity structures. And then after that, there is this information coming from this augmentation varieties. But this is just a list of properties. So if you see that all these properties are satisfied for the information then a priori you don't know whether you have the filling. I mean, it's always a matter of like constructing or non-constructing. If you know how to construct it, you can say, well, I do have it. But if you don't know, if you don't have a filling and all the ad hoc information tells you that it's possible to have it, then you can't say anything. You don't have filling, but all the information tells you it's possible. So what?
Still no more questions. Then let us take the speaker again and we know. Today, next week I can speak. Yeah.